All right, so recall a question that I asked weeks ago. I mentioned that this was about differential cryptanalysis, but actually I made a mistake there. I should say that it is related to statistical attacks, because once I said differential cryptanalysis, everybody focused on giving a difference, but idea was to, just focus on statistics. So this exercise is valid for linear cryptanalysis and differential cryptanalysis, but I said differential cryptanalysis because I was going to give an example about it. Okay, so recall the example. You are given a dice and you are allowed to roll it to see the result as many times as you want. You are asked to determine if the dice you have is fair dice or it is a biased dice, which rolls 6 with probability 1/3. Okay, for a fair dice, rolling 6 has probability 1/6. So question is, what would you do? Okay, so your aim is to come up with a solution that will solve this problem. So many of you came up with the idea saying that, okay, I will roll the dice many times and count how many times I see 6. Okay, so if you, for instance, roll it 30 times, expected value for the biased dice is 30 divided by 6, which is 5, and for the biased dice it will be 30 divided by 3, which is 10. So expected value is 5 for one of them and 10 for one of them. So if you roll it and you observe like 10 minute sixes or 12 sixes, you will say that it looks like a biased dice. But if you see low amount of sixes like 4 or 5 or 6, you will say that, okay, it looks like a biased dice. But what is the success probability of this approach? Okay, because if I roll it like 7 times or 8 times of sixes, you might say that, okay, it looks like biased, but maybe it is fair, right? Because if you say it is biased, but if it is fair, then we will call it a false alarm. But if it is biased, but you think that it is fair because you were unlucky, you rolled it and observed low amount of sixes, you will say that, okay, this is fair, but it was biased, so we will say that this is non-detection. So question is, what are my non-detection and false alarm probabilities? And what is the success probability of this attack? So in other words, how many times should I roll this dice and will be confident that it is secure? So this is related to the question of cryptanalysis, where once you perform differential attack or linear attack or any cryptanalysis technique, the question is, how many data do I need? Okay, you might say that if, okay, it doesn't matter, let's do it with a lot of data, like the most number of data we can obtain. But then the problem will be, it will not be practical. So you want to find a place where data, time, and memory complexities are optimal. Lower is better for the attacker, but if you lower it a lot, then your success probability will be lower. Okay, so in order to answer these questions, let me give you some notation. P is probability of the distinguisher for the wrong key. P0 is the probability of the distinguisher for the correct key. PFA, false alarm probability. P and D, non-detection probability. And number of plaintext ciphertext pairs used to perform the attack. T, threshold used to decide whether the key counter is a candidate. So here the threshold actually means this. Let's go back to our dice example. I said that let's roll it 30 times. Expected value for the fair dice is 5, and it is 10 for the biased dice. So I need to find a threshold saying that if it is higher than this threshold, I will say it's biased. If it is lower than this threshold, I will say fair. So T here is represent that threshold. Okay. So perception, you can look at this problem in two different ways. Okay. One way is to given N, P, and P0, what is the success probability of the attack? So this means that you found the distinguisher. So you know P and P0 because you know the probability for the correct key and probability for the random permutation. And you say that if I perform this attack with this many data, what will be my success probability? Now, one way of looking at it is this. Another way to look at it is that if I found the distinguisher, so I know P and P0, and if I choose non-detection probability and false alarm probability by myself, then how many pairs do we need to perform the attack? So what should be N? So you can look at it in this way, and in literature, people looked in this both ways. And here the problem is that you can calculate this, if you choose the threshold, you can calculate these probabilities, but the problem is that the binomial distribution calculations will not be that easy. So we have M pairs and the distinguisher is observed with probabilities P and P0. So we are trying to distinguish two binomial distributions with parameters MP and MP0. However, it is computationally infeasible to calculate the non-detection or false alarm probabilities. For example, you need to calculate the probability of observing less than the threshold. So this small n should be capital N, sorry for the typo. So you have to sum all of these values. But in practice, n might be very large, like 2 to the 80. P0 might be very small, like 2 to the minus 100. So performing the summation might take sometimes millions of years, okay? So we should come up with an easier way to perform this calculation. So in literature, I generally look at two different cases. One of them is by Ali Aydin Selçuk. So Selçuk uses the fact that binomial distribution can be approximated by normal distribution when n is large enough. Okay, his formulas provide good success probability approximations for differential and linear cryptanalysis when you have the inputs n, p, and p0. Okay, so since p and p0 comes from your distinguisher, you already obtain it by theoretical means, and you choose n by yourself, put these values into Selçuk's formula, and obtain the success probability. So many papers are written like this. In the different perspective, Blondet-Gerard and Tillich uses approximations for binomial distribution directly, so they don't convert it into normal distribution, but they use a different approximation technique. Their algorithm takes these values as input and then provides you n and t. So this means what will be your number of data you need and where you should put the threshold. Okay. So these are two good ways of looking at it, but the main problem for the cryptanalysis I see in the literature is that, it's happened in a somewhat fast way. People came up with ideas and so on. So these success probability calculations are most of the time are done manually, because even these approximations sometimes are not good. So for non-experts, reading a cryptanalysis paper wouldn't mean anything. And we don't have a good book or anything that explains all of this altogether. For instance, I don't think many people implemented this algorithm. For instance, I implemented it, but it requires calculations on very small numbers. So you have to implement it using a language like C, where you perform operations on, hundreds of digits of numbers. Even when from 0 points on, you have to write maybe hundreds of digits. So most of the time, these calculations are calculated with ad hoc methods, and we are not sure if those theoretically obtained numbers are correct in practice. Okay, so currently this is not a problem, but at some point on, maybe we should re-summarize everything in the literature and provide good results for the academia, so anybody who are not expert in cryptanalysis can understand these papers and also obtain results. So if you're interested, you can go to papers by these two people and obtain the results at the end. And I strongly recommend you to implement this algorithm, because it uses two binary searches inside each other. So it is a very nice programming exercise if you're interested. And in some cases, this algorithm provides better results than this. By better results, I mean more accurate results.